Okay, so lesson 5, we're now working on some trickier trigonometric identities. So we're not going to spend too much time on this exploring part. It just shows that there are non-permissible values. So what ends up happening with something like this, the left-hand side has no denominator. It's just sine of x, so it has no non-permissible values. The right-hand side, though, we know tan is sine over cos of x. So when we look at this right-hand side, we can see that the cos of x cancels out. So it makes sense that these two expressions are equal, except that the right-hand side does have non-permissible values where cos of x equals 0. So wherever cos of x equals 0 does give us some non-permissible values, and that ends up being at pi over 2 and 3 pi over 2 if we're just looking from 0 to 2 pi. Whereas the right-hand side has no non-permissible values. So just like our rational functions, when you're working with trigonometric functions, you can have points of discontinuity or asymptotes that give you these non-permissible values, but they still always come from the zeros of the denominator. Sometimes we refer to them as restrictions rather than non-permissible values, but it just means the same thing. So this is just the summary here. Sine of x equals tan x. Cos x is an identity with non-permissible values where cos of x equals 0. The restrictions on this identity are x cannot be pi over 2 plus n pi, where n is an integer. So remember, we use the not equal to sign when we're talking about non-permissible values. Excuse me, we use equal to if we're describing asymptotes. So non-permissible values of an identity are determined by finding the non-permissible values for each side. So you need to find non-permissible values from each side. Together, they give you the non-permissible values of the identity. When determining the non-permissible values, there are two areas to focus on. All tangent, cotangent, secant, cosecant functions have non-permissible values. So tan of x and secant x both have cosine in the denominator. So their non-permissible values are where cos of x equals 0, which is at the pi over 2 plus pi n. Or if you would rather think in degrees, that's 90 degrees and every 180 degrees after that. Cotan and cosecant have non-permissible values where sine of x equals 0, because that's what the denominator is, and that is at your pi n. Sorry, I should have made n an integer here, not a real number, where n is an integer, so every 180 degrees starting at 0. If the identity has a denominator, then any 0 of the denominator will be a non-permissible value of the identity. So these are the main ones and the ones you get asked the most. There are some more complicated ones which you come across that you kind of have to deal with once you're there. So the non-permissible values are sometimes called the restrictions of the identity. In many of the examples, the restrictions are the solutions to sine of x and or cos of x equal to 0. And those are the answers there which we just looked at. So how do we go about proving an identity? Well, the most important thing is that you need to separate the two sides of the equal sign. If we're proving that something is equal, we cannot add something to both sides because we don't know for sure that it's equal. We still need to show it's equal. So you really have to work with the left-hand side and the right-hand side completely separately. The book suggests to begin with the more complex side. It really doesn't matter. You can begin with one side, you can work with both, you can work with one side, not the other. It's completely up to you where you start. If possible, use the reciprocal quotient or Pythagorean identities. For example, use the Pythagorean identities when squares of trigonometric functions are involved. If ever you see a sine squared x, cos squared x, it's good to see if is there any way I can add sine squared x to cos squared x so that I can take them out and replace it with a 1. If necessary, change all trigonometric ratios to sine and cosine. To me, this is one of the biggest hints to get started. If you're stuck, replace something with sine and cosine. Look for common denominators. What can you bring together? Is there something you can factor to bring something together? If there is sum or difference of fractions, combine as a single fraction. So this is the common denominator part. With all of these, there's not one way you can do it. I might do it one way, you may have done it another, and that's perfectly fine. So example 1, consider the statement 1 over cos of x minus cos x equals sine x tan x. Verify for x equals pi over 3. So again, to verify doesn't mean to prove it. We're just going to substitute in a value to see if these two things are equal at that value. So when we do this, and like I said, you can put this right in your calculator. You can get 3/2 there, even if it's a decimal. It's still going to tell you whether they were equal. Sorry, I need to use the right-hand side here. So sine of pi over 3 times the tan of pi over 3. Now when you punch this into your calculator, as long as you're in radian mode, you are going to get the same thing, a 3/2. Even if you're in degree mode, you'd get this left-hand side equals right-hand side. It just wouldn't be 3/2. B, use a graphing calculator to show the statement is probably an identity. So to do that, I would graph the left-hand side in F1, the right-hand side in F2. If your graphs are the same, this is most likely an identity. On your diploma exam, the most common question with this is which option is equal to the expression they give you? Well, the easiest way to do it is graph the expression they give you, graph your options A, B, C, and D, figure out which one gives you the same graph. So prove this statement is an identity using an algebraic approach. So this is where we do need to separate each side of the equal sign from each other. And it's really up to you where you're going to start. If you want to start on the left-hand side, the only thing we can try and do is bring these together, so we'd need to make a common denominator. So this gives me 1 minus cos squared x over, sorry, I should be not multiplying by cos squared x, just multiplying by cos of x, because that's what my denominator is over here, over cos of x. Well, what is 1 minus cos squared x? Well, remember, we have this identity, sine squared x plus cos squared x equals 1. If we minus cos squared x from both sides, we find that 1 minus cos squared x equals sine squared x over cos squared x. So I get here, I don't see anything else I can do with the left-hand side, so I'm going to start working with the right-hand side now. So the only thing I can think of doing here is to replace tan, or rewrite tan in terms of sine and cosine. So that is sine x over cos x. This gives me sine squared x over cos x, which is what I wanted because now these two match. So it really doesn't matter where you start. You could work with your right-hand side first until you get stuck. Then switch over to the other one. Now you kind of have a goal though. You're trying to rewrite this as sine squared x over cos x. It's really up to you whether you work with one side or the other. Do one step and then one step on the other side. It's completely up to you. Now, we do need to state the non-permissible values as well. So if we look at both sides here, the left-hand side has cos of x on the bottom. So where cos of x equals 0, on the right-hand side, I'm going to have non-permissible values. Sorry, on the left-hand side. On the right-hand side, again, the only thing in my denominator is cos of x. So I have nothing more to add. I just need to find out what these x values are. And we know cos of x equals 0 at pi over 2 plus pi n, where n is an integer. So here we write these are non-permissible values, so we're going to write x cannot equal pi over 2 plus pi n, where n is an integer. 2. Prove the identity sine x cos squared x plus sine cubed x equals 1 over cosecant x. So again, I'm going to separate the two sides. Now, the book says start with the more complex side. Sometimes I actually like to start with the simpler side, which I think in this case is the right-hand side. So cosecant is 1 over sine of x. Well, this is really 1 times sine of x over 1. So this is really sine of x. So sometimes I like starting with the simpler side because now I know there's nothing simpler than just having sine of x, and it kind of gives me a goal for what I'm going to have to do with the left-hand side. So I see here that these have a sine of x in common. So I'm going to factor it out. Well, what happens when I factor out sine of x? In here, I have cos squared x plus sine squared x. Well, that's just 1. So this becomes sine of x times 1, which is sine of x. So both are equal now. So for my non-permissible values, I need to find what was a denominator. Well, what was the denominator here? Well, cosecant was a denominator. And I need to then look for, remember that cosecant is the reciprocal of sine. So cosecant is going to be undefined whenever sine of x is equal to 0. Sine of x is equal to 0 every 180 degrees, or pi radians. So x cannot equal n times pi. Of course, where n is an integer. Okay, example 3. Consider the identity sine A plus tan A over 1 plus cos A equals 1 over cotan A. Prove the identity algebraically. So there's usually not enough room in these in the workbooks to solve this, especially if we want to try doing a table. We're going to run out of room pretty quick. So although in your notebook I'd 100% recommending doing a table, I'm going to have to kind of cheat here. So I'm going to work with the right-hand side for a second. I know cotan A is cos over sine. So cotan A is cos over sine. So 1 over cotan A must be sine A over cos A. So this kind of gives me a goal to what I'm going to have to do with this left-hand side here. So I'm just going to rewrite it here first. Okay, so I'm going to manipulate this as much as I can. There's nothing that's squared. There's no big identity I can use. So I'm going to start by rewriting it in terms of sine and cosine. So I can rewrite tan as sine over cos. So now I have this. Well, now there's nothing I can simplify yet, so I'm going to make a common denominator on... You could do the top and the bottom, but let's just start with the top and see where it goes. So if I multiply top and bottom here, cos A, this is really like it has a denominator of 1, so times cos A. So I get sine A cos A over cos A. Okay, so now I can rewrite the top over a single denominator. And now I can factor the top a little bit. So both of these have a factor of sine A in them. So I can rewrite the numerator on top there as sine A is cos A plus 1 over cos A over 1 plus cos A. Now, what's really happening here? This is sine A times cos A plus 1 over cos A times 1 over 1 plus cos A, multiplying by the reciprocal of the denominator. These two can cancel out. So this leaves me with sine A over cos A. So now I've proved that the right-hand side equals the left-hand side. So I've done it algebraically. Again, it'd be a bit neater if you had a table and you could write this all vertically instead of having to go horizontally. I just have to work with the space that they give me here. So the non-permissible values. So I need to go through anything that has a denominator. So if I look on the left-hand side, the only thing there that has a denominator is tan A. So my non-permissible values from tan A come where cos of A equals 0. So that tells me A cannot equal pi over 2 plus pi n. Okay, then I have 1 over cotan A. So this is a little bit confusing because since it's 1 over cotan A, I need to make sure that cotan A cannot equal 0, but cotan itself has a denominator with non-permissible values. So either way, though, it ends up being the same thing. All these non-permissible values come from where sine of A cannot equal 0, because cotan is cos over sine. So I need to make sure these cannot equal 0, and that happens at every 180 degrees. There's actually one more place here where we get non-permissible values, because we have a third denominator of 1 plus cos of A. So we get additional non-permissible values where this is equal to 0. So that's where cosine of A equals -1. Well, cosine of A equals -1. At pi, and then every rotation again after pi. So we want to somehow combine these. Now, some of these overlap, which allow us, right, this really overlaps with this. So that means all of our non-permissible values are pi over 2 plus pi n and pi n, where n is an integer. Show the non-permissible values on a graph of each identity side by side. So you could just draw the holes. Your graph doesn't really show it if you graph it on your calculator, but there are actually points of discontinuity at the x values on the x-axis for this one. Example 4, prove the identity secant squared x over secant squared x minus 1 equals cosecant squared x. So again, with the right-hand side, I could just remind myself, okay, this is going to be 1 over sine squared x. That's my goal. So I'm going to work with this until I get there. Now, it's tempting. People want to cross out secant squared x with secant squared x. Can't do that because there's subtraction there. Also, this always tells us what we're trying to get. So if you cross something out and you don't get what you're supposed to, then you know you've made a mistake. But you can go to your formula sheet, and you may need to rearrange something, but we have a value we can replace secant squared x minus 1 with. We can actually replace it right away with tan squared x. Okay, so now I'm just going to rewrite everything in terms of sine and cosine. And you would have got here, if you hadn't replaced it with tan squared x, by writing in terms of sine and cosine, making a common denominator, you would have gotten the same thing. So there's always more than one way of doing these. This gives us 1 over cos squared x times cos squared x over sine squared x. So multiply by the reciprocal. Cosines cancel out. 1 over sine squared x.